Hello, good morning everybody. So, today we will continue with this theories of reaction rate. So, in our last lecture we discussed this collision theory of for the chemical reaction rate. Okay. So, the last slide where we ended at was on the activation energy, that is the effect of temperature on reaction rate constant, that we were discussing this Maxwell distribution of molecular velocities, and that in collision theory it is thought that the collision between molecules are responsible for a reaction to occur, and there is a factor that with proper geometry and with a definitive amount of energy, the molecules can react through collision to produce your desired product. So, here you see that this is the plot of the number of molecules, that is, or the fraction of the total number of molecules. You can write it over here. It is better to write the probability function, that is the fraction of total number of molecules present in the mixture, and this side is your either it may be in terms of kinetic energy or the overall energy, or maybe your speed of the molecule. So, if you increase the temperature, what you get is that this blue curve is getting flattened, and you see that this, suppose if this is your activation energy, if this line corresponds to the activation energy, then when the gas molecules were at temperature T1, absolute temperature T1, then the area under the curve was like this. Okay? And as you increase the temperature from T1 to T2, and as a result of which this plot gets flattened, then you see that this is more. So, more number of molecules are there in this region because the integrated area is more. Therefore, this situation will have a better option for the molecule to react, that is through collision. Okay. So, and that is based on purely the hard sphere collision model. Next, we will move on to another theory, which is the transition state theory. Now, you see that this diagram, this is a typical diagram, that A plus B with a rate constant producing AB. Okay. Now, this is your reactant side, and say, and this is your this is a typical this it is depicted in the form that your reaction is an exothermic one. Okay. And this is your energy of activation, delta E is the energy of activation. So, you see these two are colliding as per your collision theory, but here it is a different situation, that these two will first form an activated complex of this sort having energy higher compared to your reactants, and then this will move on to this side, or maybe it will come back to this side. So, this has got equal probability maybe of passing either to this right hand side or coming back to the left hand side. Okay. So, so this is your activated complex. So, this activated complex will undergo further reaction to produce your to give your product. So, that is the idea, and so before going into the details, let us have a quick look at this partition function, because we will recur partition function. Okay. Now, molecules will have various motions. One can be translation, another can be rotation, then third one is vibration, electronic motion, and also your nuclear motions as a whole. So, so these are in terms of the total partition function of the molecule, you can write Q is a product of individual partition functions, that is trans means translation, rotation, vibration, electronic and nuclear. nuclear partition function. Okay, so and we create a system of n molecules that are in principle independent and indistinguishable. Okay, and we get an overall partition function q for the n such particle will be q to the power n divided by n factorial. That is if you look into any standard textbook of statistical mechanics or statistical thermodynamics, you will be finding this. Okay. So, these individual terms are individual partition functions. So, this is basically this whole to the power n, this whole to the power n divided by n factorial. N is the number of n indistinguishable independent molecules. So, this is your overall partition function for this n indistinguishable independent particle system. Okay. Now, partition functions of a diatomic molecule, okay, per degree of freedom. What do you mean by degree of freedom? Degree of freedom is the various types of motions that are associated in simplistic language. Okay. So, total number of independent ways you can realize. Okay. So, so that is called your various motions like translation, rotation, vibration. So, these are the various degrees of freedom. Okay. Now, translational motion can be of like this molecule as a whole is moving, means its center of mass is moving, Okay. So, that is what is called the translational motion. So, center of mass is changing its coordinate with time. Okay. Vibration is basically your center of mass is fixed at a point, and your these two masses of a diatomic molecule, I mean these two atoms, they are changing their position. Maybe it is doing like this motion. Okay. So, that is why this is called your vibration. So, during vibration there should not be any change in your center of mass. So, center of mass is remaining fixed. So, to keep your center of mass fixed, these two molecules, or I mean these two atoms will have to move in a definitive fashion, so that there is no net change in the position of your center of mass. Okay. And in case of rotation, it is basically about some axis this molecule is rotating. So, this is changing its position this way, and this other one is also doing like this. So, and translational partition function, it has got this expression, and where L is the box length, it is per degree of freedom. Okay. And it is generally very high for a reasonable size of L means box length. For H2 it is of this sort, I mean 10 to the power 10 per meter at 500 Kelvin. For CO it is 10 to the power 10, it is also 10 to the power 10 order. Cl2 it is of the order of 10 to the power 11. So, it is proportional to mass, directly proportional to mass, I mean to the power half, mass to the power half, and temperature also to the power half. Okay. And it is in reverse sense, I mean although H is constant, so it is a constant quantity, and L will is here. So, basically it depends on M and T. Okay. That is why as M increases, it is increasing. Here also M increases, it is increasing. H to M is less, therefore it is 1.8. Next is vibration. It has got this expression 1 divided by 1 minus e to the power minus h nu by kBt, where kB is Boltzmann constant, and usually it is equal to 1 unless vibrations are of very low frequency. Very low frequency means nu is high, means it is very less. So, if this is a low, or maybe if h nu, this h nu is much smaller compared to kBt, then this term this has got some 1 by something. So, it is a this, if it is much smaller, then practically you can approximate this to something. Okay. Or maybe for simplistic language, if this is very low frequency mode, then this will have value something a little more, because as you reduce this, as I was telling that if h nu is less, then this will be less than 1, this whole thing will be less than 1. So, that means this will be more than 1. So, that is why it is increasing. Okay. So, low frequency vibration when it is introduced, then this corresponding vibrational partition function increases. Rotational partition function, it is large, it is for H2 it is 2.9, CO it is 180, Cl2 it is 710. So, partition function for per degree of freedom, it is of this order, but it is higher than this one, but not higher than this one. Okay. Now, expression for various thermodynamic quantities, chemical potential. Okay. It is having this expression where Q is the total partition function, is having this one at constant volume and temperature. Here it is constant volume and number. P, it is of this expression. Internal energy is having this expression, where Q is Q to the power n by n factorial, as I mentioned earlier. Okay. Now, move on to a reaction of this kind, A plus B giving rise to C plus D, with stoichiometric coefficient nu A, nu B on the left hand side, and right hand side nu C and nu D. So, equilibrium constant at a temperature T, you can write in this way. Okay, you can write QC partition function per unit volume, of course. Okay, QC by V to the power this one, QD by V to the power nu D, divided by this into KT by P0. Okay, why KT by P0? You can directly, okay, let us go back to the earlier slide. Okay. So, so basically this will be having this expression, P is basically your this one. Okay. So, if you write the appropriate expression, you will be getting this type of expression, that it is Pc by P0 to the power nu C, Pd by P0 to the power nu D, Pa by P0 to the power nu A, Pb by P0 to the power nu B. So, it is a kind of activity P by P0, it is a dimensionless quantity. So, activity of C to the power nu C, activity of D to the power nu D, activity of A to the power nu A, activity of B to the power nu B. Okay. So, this is the expression for the equilibrium constant at a temperature T. Okay. Now, we will try to apply these expressions at the appropriate places. Okay. So, let us start with the transition state theory, that a simple reaction A reacting with BC producing AB plus C, that is an atom exchange reaction, maybe say. Okay. So, it is going via an activated complex, or it is going via a transition state. Okay. So, that is why it is called the transition state theory, or TST, and it was first developed around 1935, and it has also been known as absolute reaction rate theory. Also, it is known as activated complex theory, although these two names are outdated now, and transition state theory is nowadays used. This term is nowadays used. Okay. So, there is a typical potential energy surface that it is an cross section. This is a three dimensional description, energy this way, this side RAB, this side is RBC, that is distance between B and C, and this is distance between A and B. Okay. So, you are plotting in a three dimensional way, that this side is your energy of the product, or energy of the process, overall energy of the process, and this side your distance for AB, and this side is distance for BC. Okay. And this is called the transition state, where this ABC is located, that is this one is located, this ABC is located. Okay. This is the subtle point, that is this is your transition state, this is your reactant side, this is the product side. It is just like a two mountains separated by a valley. So, this way reactant will move this way to the transition state, and then it will pass to the other side, or maybe it will come back to the reactant side. It is just like your you find saddle in case of horse riders generally use this. Anyway, rate constant of the reaction, what is the rate constant? How will you write that? Rate constant of the reaction is the number of activated system, that is activated complex, activated, you can say that activated molecule. Okay. So, the number of activated molecule that are, or activated molecule, or maybe you can say that is ABC that I was telling. So, number of activated complexes passing per second through the top of the potential energy barrier. So, you are here, like you started from here and then you moved to this one and then you are here. So, this is your reactant side, this is your activated, and this is your product side. Okay. So, it is basically reaction rate is nothing but the number of this species passing per second through the top of your potential energy barrier. Okay. And this is equal to the concentration of the activated complex times. So, this is equal to, this rate is equal to number of the concentration of the activated complex times the frequency with which, say nu is the frequency with which the activated complex is passing, this one, or the average frequency with which this activated complex is passing this top. Okay. So, your velocity is equal to nu times concentration of the activated complex. Okay. Concentration of the activated complex. So, basically it is A plus B, it is a quick equilibrium, Kc, your it is a fast equilibrium, then giving rise to X double dagger, and then K1 slow, it is the slowest step, then giving rise to product. Okay. For that I have written V is the reaction rate, which is nothing but equal to nu times C double dagger. So, the same thing, that this is your scheme, this is the scheme. Okay. Now, this activated complex, this one is in equilibrium with reactants. So, equilibrium constant Kc can be written as this divided by this in terms of concentrations, concentration of the activated complex divided by the concentration of A and concentration of B. So, you can write C, that is the concentration of the activated complex, equal to Kc into Ca into Cb. Okay. So, you just write then the appropriate expression, that velocity of the reaction is equal to nu is the frequency with which it is passing the top of the barrier times Kc times Ca times Cb. Okay. And we know that V is equal to minus dCa dt, which is equal to K times Ca Cb. Okay. Therefore, we can write rate constant K is equal to nu times Kc. Okay. Kc means it is basically equilibrium constant for this activated complex formation. So, you can also put a double dagger on Kc. Okay. So, we are involving this activated complex in this equilibrium process with your reactant side. Next, from statistical thermodynamics, we can write your equilibrium constant Kc is equal to Kc double dagger, or maybe you can write Kc as well. So, Q double dagger, it is star divided by Qa star. Okay. Then Qb star. Okay. And Avogadro number La e to the power minus delta E by RT. Okay. So, ultimately K is equal to nu times K C nu Q QA LA minus delta E by RT, where delta E is delta E is E double dagger minus EA minus EB. Okay. So, here this Q double dagger with star is the partition function per unit volume of the activated complex. Okay. And of course, it is one of its vibrational degrees of freedom is in the act of passing over to the translation along the reaction coordinate. So, one of its vibrational degree of freedom, suppose if it is a complicated molecule or maybe complicated entity, the idea is that out of many vibrational degrees of freedom, okay, only one vibrational degree of freedom will be responsible for making this activated complex to pass the the top of the barrier. Okay, that is why one of its vibrational degrees of freedom is in the act of passing over to the translation. That is, that vibrational degree of freedom is supposed to be a loose vibration, and that will be converted to a translational motion. Unless it is converted to a translational motion, it cannot in principle pass the barrier. Okay. So, it is in the act of passing over to the translation, okay, along the reaction coordinate. So, the partition function for the only vibrational degree of freedom that is responsible for such passage from one side to the other. Okay. So, that we can write in this way, that if V double dagger star, which is equal to 1 by 1 minus e to the power minus h nu, suppose its frequency is corresponding frequency, vibration frequency is nu, therefore, we can write, and since nu is very small, we can approximate this to, we can approximate if nu is small. As I told you that generally this vibrational partition function, these are generally unity, close to unity, but if these modes are, I mean this frequency is low, then it will not become 0, but it will be something else, okay, something else, it is more than 0. Therefore, your number will be, this denominator will be less than unity, 0 and 1, between 0 and 1. Therefore, this overall f nu double dagger star will be basically it will be little more than 1. So, you can you can write in place of this, approximate this to, when nu is small, you can write your this one to be equal to 1 minus h nu divided by k b t. Therefore, this will be basically, this will come out to be basically equal to k b t by h nu. Okay. So, your q star double dagger will be equal to 1 vibrational mode less. So, it will be f v double dagger star times q star prime. This prime means 1 mode less. Okay. So, therefore, k, you can write k equal to nu into k b t by h nu. Okay. Then q double dagger star primed divided by q a star q b star, because these are the, and one thing, these do not have any loose vibrational mode, because maybe these are atoms. So, there is no question of loose vibrational mode. into LA times exponential quantity. Okay. So, this gives you Kb T by H into Q divided by Qa Qb star La times exponential quantity. Okay. Now, if you take Kc double dagger is equal to, now if you take this one prime divided by Qa Qb star La exponential minus delta E by RT, then you can simply write K rate constant is equal to Kb T by H into Kc this one. Okay. So, Kc double dagger is like the equilibrium constant, but with one vibrational degree of freedom less of the activated complex. So, this one is having 1 degree of freedom less, because that degree of freedom is responsible for the reaction to take place. So, that is converted to a translational mode, and that translational mode will help in making your activated complex to pass the top of your barrier. Next, this Eyring equation. So, this last equation, this one, Eyring equation and relation with thermodynamics. Let us consider a bimolecular reaction under transition state theory, okay, such that A and B, okay, they are in equilibrium with your activated complex X double dagger. Okay. The forward equilibrium, this one is having the equilibrium constant Kc, and it is this equilibrium is established very fast, and then this X double dagger slowly passes to the product side with a rate constant K1. So, K rate constant is equal to Kbt by H into Kc double dagger. Okay. As we just have deduced it, where Kc double dagger is equal to C double dagger divided by C and C, which is simple concentration equilibrium constant. If we want to convert this to activity equilibrium constant, that is true thermodynamic equilibrium constant, then we have to use the corresponding activity term, that is we have to divide C double dagger by corresponding standard concentration and also these two by standard concentration, like this. Okay. So, Kc double dagger with 0 bar, it is 0 bar, is equal to this. Okay. Therefore, we can write that for this type of reaction A plus B giving rise to X and then X giving rise to product, we can write Kc double dagger with is equal to Kc double dagger 0 bar divided by C 0 bar. So, this is the relation between concentration equilibrium constant and the activity equilibrium constant. Okay. That is, you are dividing this concentration to make it dimensionless, you are dividing by C 0 bar, you are dividing by that. Okay. So, you have got that delta G, this is this simple thermodynamic expression, delta G 0 bar with double dagger is equal to minus RT ln Kc this bar. So, because we will be using this expression over there, okay, is equal to delta H minus T delta S with double dagger and 0 bar. Okay. This gives you Kc double dagger bar is equal to e to the power minus delta G double dagger 0 bar divided by RT, which is equal to e to the power delta S double dagger 0 by R into e to the power minus delta H double dagger 0 by RT. Okay. So, therefore, we have come to a relation that your equilibrium constant that describes the equilibrium between your reactant and the activated complex. Okay. So, that is Kc double dagger with 0 bar is equal to e to the power, that is this, there are two exponential quantities. One is this one, it does not have explicit temperature dependence, and it has got an explicit temperature dependence. Okay. So, it has this entropic term. Okay. So, standard entropy of activation, it is the standard entropy of activation, this is the standard heat of formation for the activated complex. Okay. So, from this we can write K is equal to kBT by H, okay, divided by C0 bar, because you go back to the earlier slide, this one, okay, because you have got Kc double dagger is equal to Kc double dagger 0 bar by C0 bar, that is why this one divided by C0 bar. Okay. So, this gives you kBT by H C0 bar, okay, into e to the power delta S. So, this exponential to the power delta S quantity and exponential to the power delta H quantity. Okay, that is an entropic term and is an enthalpic term. Okay. Now, we have this K is equal to kBT by H into Kc, this one. Okay. This one, we have got this one, this expression. So, we will be using it again. Okay. So, what we have to do is we have to take logarithm of both the sides. Okay. Taking logarithm of both the sides, and then we will differentiate it. So, what should we be getting? Okay. Basically, we take logarithm of this both sides. So, ln k is equal to ln kb by h, then plus ln t plus ln kc double dagger. Okay. Okay. So, then let's do it. So, k is equal to kb by t h kc double dagger. Okay. So, ln k, that is your rate constant, is equal to ln kb by h plus ln t plus ln kc double dagger. Okay. So, this is the constant quantity. Okay. So, if we do differentiation with respect to T, that is the temperature, then d ln k dt, because we will ultimately relate this with, or we will ultimately compare this with your famous or well known Arrhenius equation. Okay. So, d ln k dt is equal to, this one will be 0 plus this is d dt of ln t is 1 upon t plus d dt of ln k c double dagger. Okay. So, we can write, d ln k c double dagger dt is equal to delta E or delta U, whatever. This is called your iso core. Okay. So, we have got this expression, this is another Van 't Hoff expression. So, now what we will do, we will plug in this expression over here and then we will try to simplify it. Okay. So, this is one Van 't Hoff's expression and this is the expression after differentiating the logarithmic form of this expression, this one. Okay. So, comparing these two, what we are getting is this, d dt of ln k is equal to 1 upon t plus delta u 0 bar divided by RT square is equal to RT plus delta u 0 bar divided by RT square is equal to your RT plus delta H 0 minus P delta V. 0 bar divided by RT square. Okay. So, what is that? We have to find it out, find it. Okay. So, now we let us write the well known, all of you know, or all of us know this Arrhenius equation d dt of ln k is equal to EA by RT square. So, now we are in a position to compare this with this one, because left hand side this one and this one, these two are identical. So, we are in a position to compare. So, what do we get? That EA is equal to RT minus delta H plus delta H double dagger 0 bar minus P delta V. Okay. So, this is enthalpy of activation, this is volume of activation, standard volume activation, this is standard enthalpy of activation. Okay. Now, what happens? There are situations. One situation is for liquid phase reaction, liquid phase reactions, okay, where your change this P delta V, this volume activation may be neglected for all practical purposes. So, that means for liquid phase we have a very simple relation that EA is equal to RT plus delta H double dagger 0 bar. Next, what happens for your gaseous reaction? This is your liquid phase. What happens for gaseous reaction? That is reaction that is your left hand side A plus B, all are gas, giving rise to C plus D, all are gas. Okay. So, what is the situation? So, for that we have to apply this ideal gas principle. We have to assume that these gases behave ideally. Okay, these gases behave ideally. So, basically you have say N1 mole of A plus B of N2 giving rise to say for example say 1 mole of activated complex, say 1 mole of activated complex. Okay. So, basically your right hand side is less, right hand side is 1 and left hand side is N1 plus N2. So, let us write in place of N1 plus N2 equal to N. So, left hand side total number of moles will be N and right hand side total number of moles will be N, because out of these two species A and B, your activated complex will be produced. That means, N1 mole of A and N2 mole of B producing 1 mole of the activated complex. Okay. So, for your gas phase reaction, your P delta V term double dagger 0 term will be equal to 1 minus N into RT. That is at a given temperature PV is equal to N RT. Okay. That is that you have to use. Okay. So, that is P delta V is the delta V, that is the change in volume because of this activated state formation, activated complex formation, there is a change in volume. So, that change in volume can be computed this way, assuming these gas molecules are behaving ideally. Okay. From your PV is equal to N RT, this expression. Okay. So, basically P delta V is equal to delta N RT at a given temperature, because you are carrying out this reaction at a fixed temperature. So, that is why P delta V, so P delta V double dagger 0 bar is equal to your delta N double dagger 0 bar RT. Now, this delta n is nothing but your final minus initial, final is 1, initial is n, okay, where n is the this step. So, this step is you can call this as this step you can call as like an elementary step. In this elementary step your activated complex is formed. So, therefore, molecularity of this particular step, that is the step in which your A plus B giving rise to activated complex, will be n 1 plus n 2 or maybe n, molecularity n, that is n number of molecules are involved in the production of 1 mole of your activated complex. Okay. Therefore, if it is the case of a bimolecular gas phase reaction, gaseous reaction, then you can write E A is equal to delta H double dagger 0 bar plus, so 1 minus n, okay, 1 minus n RT, and there is another RT term plus RT. Okay. So, for your bimolecular case it is 2, therefore, delta H 0 bar is equal to, delta E A is equal to delta H 0 bar plus RT, that is equal to 2 RT plus delta H 0 bar. Okay. Therefore, we can write, what can we write is this. So, let us again go back to the expression of K. Expression of K will be K is equal to KBT by H C 0 bar e to the power delta S double dagger 0 bar by R into e to the power minus delta H 0 bar by RT. This is your expression for K. Okay. So, what you have to do, we have to now plug in this appropriate expression. Okay. Since it is 2 RT, so additional e to the power 2 terms will come into picture. Okay. So, that is why your expression will be, your K will be KB T divided by H C this one into e to the power delta S, whatever was there is there 0 bar by R e to the power minus delta H 0 bar by RT times e to the power 2 RT by RT. Okay. So, that will give you E square. Therefore, your K is equal to KT by H divided by C 0 bar e to the power this, e to the power delta H, e to the power delta S term, e to the power delta H term times E square. Okay. So, for a bimolecular gas phase reaction, you are getting an expression of this sort. Okay. Next is we have to compare this with collision theory, because we already have started collision theory. That collision theory is purely based on hard sphere approximation, that these hard sphere molecules are reacting via collision with one another like this. Okay. So, therefore, if we look into the pre-exponential term, that is A, that we already have talked about, A is equal to P is the probability or steric factor into Z A B, small z A B, which is equal to K B T divided by H C 0 bar E square, then e to the power delta S double dagger 0 bar by R. Okay. If we compare compare this with this one, then what do we get? Okay. We get ZAB, small ZAB is equal to KB T by H C 0 bar into E square. Okay. So, therefore, this frequency term, okay, this frequency term is basically this term, okay, and you see that frequency term increases with increase of temperature, and it occurs in a linear fashion. Okay. Now, what about the other term? This other term is e to the power delta s double bracket 0 by r. So, which you can just equate to your P, that is your steric factor. Okay. So, therefore, this steric factor, you see that if you write that your steric factor is this, equal to delta S double dagger 0 by r, okay, this steric factor, then you can see that this exponential to the power delta S activation, that is entropy of activation, has got a relation with the steric factor. Okay. So, entropy of activation means standard entropy of activation, of course. So, standard entropy of activation means you have got your reactant, that is A and B, and you have got your product, or product means your activated complex. Okay. So, so if you just look into this situation, that your A plus B giving rise to your activated complex, then if this is giving rise to activated complex, then it is basically you are having two atoms over here or two molecules over here, and you are generating a single molecule. Single means only one species on the right hand side. So, there is a net decrease in entropy of the system, just if we concentrate onto the system. Okay. So, this factor has got enormous importance onto this onto the behavior of this reaction, that is whether if we have a collision, like if we try to have a link with your collision theory and absolute reaction rate theory, then if there is a collision between these two molecules, then and if they are not properly oriented, okay, if they are not properly oriented, then they will not make any product, they will not give rise to any product. Okay. So, that is very important. So, this entropy factor has got also an important role, okay, important role in determining your this pre-exponential term. So, pre-exponential term has got this your frequency term, okay. Another is your steric factor or maybe entropic term. Okay. So, this entropic term is very important. So, and you see that as such, this entropic term e to the power delta S double dagger 0 bar does not have an explicit temperature dependence. This exponential term, it does not have any temperature over here. Maybe delta S double dagger bar, this quantity is having some, maybe it will have some temperature dependence, but no, that is not the, it is not directly or maybe explicitly showing anything. Okay. So, comparing with collision theory, we get that your this, if we again go back to the earlier slide, that you see that your activation energy has got an RT term, an enthalpic term, and also a kind of pressure volume work kind of term, P delta V kind of term. Okay. So, if there is an activated complex formation, then there is a reduction in number of moles, and this reduction in number of moles, okay, is ultimately related to maybe a reduction in the work done by the system. Okay. And for your liquid phase, this one, this P delta V, this volume of activation term times P is very close to 0. Okay. Therefore, it is simplify, it is getting simplified to this type of expression, but your gas phase reaction, since it is a huge volume change during reaction, therefore, your this particular term really matters to the overall energy of activation term. Okay. And if you call this particular your activated complex formation as an elementary step, then your left hand side number of species, that is if there are 2 species, 2 molecules, then it will be a bimolecular reaction, bimolecular elementary reaction. Okay. So, if for a bimolecular gas phase reaction, gaseous reaction, your activation energy will be your delta H is 0 bar double dagger plus 2 RT. So, 1 RT was there and another RT is coming as a result of your work done, okay, work done by the system. Okay. So, ultimately we get this expression. So, what have we learned from this lecture? That your this is a typical reaction, a bimolecular reaction, maybe if you think of a bimolecular. So, it is a typical bimolecular reaction. These are activated complex is forming. This side is a reaction coordinate, maybe as a function of some distance between say A and B. Okay. We talked a little about partition function, and these partition functions basically combination of your various terms arising out of various motions. One is translation, another is rotation, vibration, electronic, and of course nuclear partition function. This partition function is basically representing a number, it is basically a number. Okay. So, how the particles are partitioned between various level at a different temperature and at some temperature. Okay. Now, we have given some estimate of partition function per degree of freedom for a diatomic molecule. Okay. Next is expressions. We just wrote the expressions for various thermodynamic functions like chemical potential, entropy, internal energy and pressure, and with that we wrote an expression for your equilibrium constant at a temperature T. Then we started with transition state theory. Now, this transition state theory is, the idea is that there is an activated complex of this type is formed, okay, and then it will dissociate or it will give rise to product. And the idea is that in this activated complex, since this is a kind of aggregate, say ABC aggregate, it will have various vibrational modes, of which one is a weak vibrational mode, and that vibrational mode will be converted to a translational mode. That is, that vibrational mode, it's a low frequency and maybe a large amplitude vibration that is responsible for the rupture of a particular bond or the rearrangement of a particular bond, giving rise to AB plus C. And that we did in this fashion, that this is your scheme, then we wrote the equilibrium constant. Then this equilibrium constant is written in terms of various partition functions. Then and also we have taken out one particular vibrational mode. So, this vibrational and corresponding partition function, and therefore, we wrote your partition function for your activated complex in terms of another partition function times one vibrational partition function. Okay. Then we got this expression, and finally, we compared with your compared with collision theory, and this says that your this entropic term and this term Kb by THC, this term is similar to your A term, similar to your A means free exponential term, and your steric factor is in principle related to your entropy of activation. Okay. So, in this discussion we have learned how learned the treatment of your reaction rate based on transition state model. So, next day we will have the extension of the same theory for surface reactions and some other aspects as well. Okay. So, till then have nice time and see you in the next lecture. Thank you.